All right, let's talk about category theory. You've probably heard the name thrown around, right? It sounds like this super intimidating, abstract math thing that has nothing to do with writing code. But what if I told you it's actually one of the most practical toolkits we have for building modern software? Well, today we're going to pull back the curtain and demystify it.
So, why should you even care? To get to the heart of it, we need to look at the problem we're all facing. Bartosz Milewski has this great quote. He says, "Our whole industry is in a phase transition." Think about it like this. We're all frogs swimming in a pot of water that's slowly getting hotter. And we have to ask ourselves, is it time to jump out and find something new?
You know, for a long time, the old way of doing things was fine. Back in the day, we had single-core processors. So thinking step by step, imperatively, that made total sense. But just look at the new reality. Everything's different now. Multi-core chips are everywhere. And our old ways of managing state, well, they're just not cutting it. They're falling apart under the pressure, creating a nightmare of data races, deadlocks, and just a mess of complexity that's almost impossible to manage.
So that's the big takeaway here. The ground has literally shifted beneath our feet. The hardware changed, but our thinking didn't keep up. Our old tools are at their breaking point, and if we want to build software that's actually reliable and can handle all this concurrency, we desperately need a new foundation. Okay, so if the old ways are busted, what's the answer? And this is where it gets really interesting. The solution isn't just another shiny new framework, it's a whole new way to think. And that's where category theory comes in. It might have this reputation for being just abstract math, but it's really a treasure trove of incredibly useful ideas for programming. It's a fundamental shift in how we approach building software.
All right, let's dive into the core idea. Let's see how this whole thing is built. And we're going to start with a concept that's, believe it or not, described as embarrassingly simple. So forget all the scary math for a second. When you strip it all away, category theory is about one thing, and one thing only: composition.
So what is a category, really? At its heart, it's just two things. A bunch of objects, you can just think of them as dots, and a bunch of arrows that connect those dots. That's literally it. But the magic, the entire power of the system, comes from one single crucial rule.
And here's that rule. It's super simple. If you have an arrow that gets you from A to B, and you have another arrow that gets you from B to C, then the category guarantees, and I mean it's an ironclad guarantee, that a direct arrow from A all the way to C must exist. This is the law of composition. It's kind of like a flight itinerary. If you can fly from New York to Chicago, and then Chicago to LA, you know there's a complete journey from New York to LA.
Now, I know that sounds almost too simple, right? But that single guarantee, that promise of composition, that is the bedrock. Everything else we're going to talk about is built right on top of this one idea. It's the source of all its power.
Okay. Dots and arrows, that's all well and good. But what does this have to do with the code we write every single day? Well, let's make it concrete. Let's talk about something called the category of types. And the cool part is, it's something you already use all the time, even if you don't know it. It works like this. In this category, the objects are just our programming types. Int, string, bool, all the usual suspects. And the arrows, those are just our functions. So if you have a function that takes an int and returns a string, well, in category theory, that's just an arrow pointing from the int object to the string object. Simple as that. And here's the mind-blowing part. That law of composition we just talked about, you enforce it every single time you write code. Think about it. You can't just take a function that returns a string and plug its output into another function that's expecting an int, right? What happens? The compiler yells at you. It throws an error. In a way, your compiler is already acting like a category theory verifier, making sure your arrows line up.
Now, this is all great for what we call pure functions. Simple functions that just take some input and spit out some output. But let's be real. The real world is messy. Our functions don't just do that. What happens when they have to do other stuff? Side effects, like writing to a log file or making a network call, or maybe they can fail and throw an error. Let's look at a classic example to see what I mean. Imagine you have a couple of simple functions you want to chain together. But here's the catch. Each one also needs to write a little message to a log saying what it did. How do you compose those?
Well, the old school way, the messy way, is to just have the function secretly write to some global logger somewhere. But that's a nightmare for testing, and it completely falls apart when you have multiple things running at once. So the category theory approach is totally different. It says, don't hide the side effect, make it explicit. Our function doesn't just return a bool anymore, now it returns a pair, the bool result and the log string.
The side effect is no longer hidden. It's right there in the return type.
But wait a second. This creates a new puzzle, right? Our functions don't compose nicely anymore. The output type of one doesn't match the input type of the next. And this, right here, brings us to the most famous and most feared concept in all of this: the monad. And what is it? It's just a pattern. It's a recipe for the glue that lets us stick these new, embellished functions back together in a clean, predictable way. I love this quote. The monad is like duct tape. It's not some mystical, philosophical concept. It's a really practical tool. It just glues things together. So whether that extra context you're carrying around is a log string, a possible error, some state, or an async promise, the monad is the pattern that lets you compose them. It's just composition, but for the real messy world.
Okay, so we've got the core building blocks now: categories, composition, and even monads. But let's zoom out for a minute, because this is about more than just a few coding patterns. This is about a completely different way of thinking about our software. You see, with traditional imperative programming, we're always stuck thinking about the tiny details. We're constantly thinking, okay, first do this, then change this variable over here, then loop through that. We get bogged down in managing every little step, every little state change. And as our programs get bigger, trying to keep all that in your head becomes, well, pretty much impossible. But category theory offers a totally different approach. It's more global. Instead of focusing on the step-by-step, we declare the big picture. We use composition to build a data pipeline. We say, I want the data to start here, go through these transformations, and end up here. We describe what we want to happen, and we let the composition handle the how. It's a massive shift in perspective.
There's this really powerful analogy that's used to describe our situation. Think about a lot of the critical software we rely on today. Operating systems, huge web services. They're like the Beauvais Cathedral in France. Absolutely breathtaking, a marvel of engineering. But it was built on really flimsy theoretical foundations. And to this day, it needs all these extra supports and patches just to keep it from collapsing.
And that really forces us to ask a tough question. If our software systems are cathedrals, what are our foundations made of? Category theory isn't about learning a bunch of clever new tricks. It's about giving us a solid mathematical foundation for composition. It's the kind of bedrock we desperately need if we're going to build the next generation of software that's reliable, scalable, and can handle the concurrent world we live in. So the real question is, are we ready to stop building on sand and start building on solid rock?